Alright, good night everyone. It's time to get started. So let's go. Alright, I need to settle my mind on this. This is where we are right now. We have to continue implementing the rest of the instructions of the chipset. This is the part of the tutorial where we are out of instructions. Draw some circles and draw the rest. Implementing the rest of the 6502 CPU instructions should be relatively straightforward. I won't go into detail for all of them, just some remarks. ADC is perhaps the most complicated instructions from a logic law perspective. Note that the spec contains details regarding decimal mode that can be entirely skipped because the RICO modification of the chip didn't support decimal mode. After ADC is implemented, implementing SBC becomes trivial as I minus B equals A plus minus B, and minus B equals not B plus 1. PHP, PLP, and RTI have to deal with 2-bit B flag, except for interrupts and executions. Those are the only commands that directly influence or being directly influenced by the 5th bit of the status register B. The majority of the branching and jumping operations can be implemented by simply modifying the program counter register. However, be careful not to increment the register within the same instruction interpret cycle. So here goes nothing. So the first thing I want to do is getting my reference page, and let's start from the top to the bottom. So the first we are implementing is add with carry. These instructions adds the content of a memory location to the accumulator together with a carry bit. If overflow occurs, the carry bit is set. This enables multiple byte addition to be performed. Processor status after use. It changes carry. 0 is set if accumulator is 0. Overflow flag is set if sign bit is incorrect. What does that mean? Negative flag set if the 7th bit is negative. So overflow on bit 7. I will need to investigate a little of this. But let's try to get started. So we already have some instructions. Where is my music? So we have increment on X and Y. So we have increment register in here. So one thing I wanted to do was moving these functions to the base class, but I will wait until later because I want to check how to do the updating of the flags. So to get started, let's put a comment here for what we are doing. Func add with carry to register. So we have the register and the addressing mode again. So we will get the address the same as before, get the memory, get the value from the address, and this is where things starts to change a little. Let's do bar result. It's an integer and it equals to p register value plus value. So now that we have the full bits, 64 bits integers, we can start trying to inspect what changed with this. So so we can use first let's set the register value. It is going to be result and OXFF. If I am not correct, this is an 8-bit register, so this works, right? So we can update 0 negative flags using this function, using the result. And now I need to update the carry flag. No. So I need to update the carry flag and the overflow flag. So let's try to check what they mean. The carry flag is set if the last operation causes an overflow from bit 7 of the result to an underflow from bit 0. This condition is set during arithmetic comparison and during logical shift and can be explicitly set using set carry flag instruction and cleared with clear carry flag. So what I am trying to understand here is this integer treated as an unsigned integer, or is tried as a signed integer? Because it maybe what we need to check is so let's make a function update C flag with the result. Func update C flag with our value. And what I understand here is I can create a variable did carry that is a boolean, and this can be p value and 0xFFFF. Should I use all the 64? Nah, no, right? There is no need. So I can just say flags.c equals did carry. So that should work. Okay, let's hope this works as expected. So now let's see what is the overflow flag. The overflow flag is set during arithmetic operation if the result has shielded an invalid 2s complement result. Example, adding two positive numbers and ending up with a negative result. Ah, I see. This is determined by looking at the carry between the bits 6 and 7 and between 7 and the carry flag. So, I think for the overflow flag we need the previous and next value. So let's add a function, update, what's the name of it again? B flag. Let's name it before. So why don't we try to search for examples? This is overflow flag examples. Overflow flag. Let's turn it off. The rules for turning on the carry flag in binary integer math are true. The carry flag is set if the addition of two numbers causes the carry out of most significant leftmost bits added. So that I understand that, and is what I did, I think. The carry borrow flag is also set if the subtraction of two numbers requires to borrow into most significant leftmost bit subtracted. Otherwise the carry flag is turned off. So this case is not. Oh, actually it is, because this will be a plus 1110 and it will cause a 10111. So mathematically it works because it will add the complement. In unsigned arithmetic, watch the carry flag to detect errors. In signed arithmetic, the carry tells you nothing interesting. Overflow flag. The rules for turning on the overflow flag in binary integer math are true. If the sum of two numbers with the sign bits off yields a result number with the sign bits on, the overflow flag is turned on. So I see. If the sum of two numbers with sign bits on yields the result with number with the sign bit off, the overflow flag is turned on. And what happens if they are different? So it seems they are off. So only when they are the same and the result is changed. So all of these cases they are off. Wait, but why? Because it didn't change the bit. Note that you only need to look at the sign bits leftmost of the three numbers to decide if the overflow flag is turned on or off. So I need the three numbers. If you're doing choose components, signet arithmetic overflow flags on means the answer is wrong. You added two positive numbers and got a negative, or you added two negative numbers and got a positive. If you are doing unsigned arithmetic, the overflow flags means nothing and should be ignored. For more clarification, please refer to this. So, what does this mean? So, 1000. So I think this is wrong. This one should be on. I am adding these numbers. Do I have something in the calculator for this? I don't see anything about flags. Okay, no, it will not work. So I am not entirely sure of how this works. Let's try another source. So this one, they are trying to make him not look at the flag. Each flag can occur on its own or both together. The CPU's ALU doesn't care or know whether you are doing signet or unsigned mathematics. The ALU always sets both flags properly when doing integer math. If your program treats the bit in a word as an unsigned number, you must watch to see if your arithmetic sets the correct flag on, indicating the result is wrong. And this is the part I don't get. Well, what does mean the result is wrong? It means you have to add 1 to some other byte. The overflow flag is only relevant to signet numbers, not unsigned. If your program treats the bits in a word as choose complements signet values, you must watch to see if your arithmetic sets the overflow flag on, indicating the result is wrong. You don't care about current flag when doing signet. Yeah, but I want examples. The sum of two numbers with the sign bit off yields a result with signed bit on. The flag is turned on. So let's name this to A and B, and name this result. So we will for now, let's try to make it hard-coded. So we want to check let's try to make a constant. So this is the single bit equal to this 3, 4, 5, 6, 7, 8. Okay. This is an integer. So if PA and the sign bit is equals to PB and the sign bit and P result and sign bit is different to PA and sign bit, that means the flag is set. I assume otherwise the flag is unset. Alright, this is dot value. And this one carry is also dot value. So let's see if this matches. So if they was the same and the result is different, it is set. Why is this an error? It's flags, not flag. Okay. Let's check if this is correct. So this was 0 and 0 and the result is different. This was 1 and 1 and the result is different. And this case is on. This is 0 and 0 and the result is 0. So it's off. 0 and 1, they was different and you don't care. 1 and 0, they was different, so you don't care. 1 and 1 and the result is still the same, it is off. So yes, this most likely makes it up. Awesome. So we have carry flag and overflow flag, and we can use them for our operation. So we have update C flag and update B flag, and for the B flag we need previous value B register dot value value and the results. So I am doing it before setting the actual value because it should not matter the order. This is a single instruction anyway. Otherwise I could save it in here, bar previous int equal, and get the register value, and this is should for the sake of for having stuff ordered, so I have all the update flags after the actual operation. So I should make tests for this now, and this is the part that I don't like, because I have to make my mind on how this works. How is this? Name it ABC. So, let's make a new function. How is the name? Right, so I have to come here and check what are the opcodes. 0x69 for immediate. $0x69 ADC add with carry. Let's create a new group of tests. Func test ABC, was it? Yeah. Add with carry, and we are testing this function, and let's call this function after the SDA group. Okay, our test setup is ready, and now I have to make duplicates of this and get the rest of the number. So I will move this for a moment to my other monitor, and we'll start changing some values here. So this one is 65. Alright. So no, this is not what I want. So I want to copy this because I want to have the addressing mode written in my test. This is my ABC 0 page. This is not store data. This is add with carry. Let's see. So 0 page is 65. Wait. 0 page is 65. This one I wrote 69 is for immediate. Absolute is 6D. Zero page X is 75. 0x what? No, this is absolute X is 7D. Absolute Y is 79. Indirect X is 61, and indirect Y is 71. So let's see, do we have all of them? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Okay, awesome. Now let's copy this and let's move to the bottom, paste this, and create a function statement. Okay, so it compiles again. So let's create a print for the first one, and now we can before making the test, let's actually register the instruction. So basically we have to create our ABC instructions in here. So let's duplicate one of these lines and let's change this for ABC. Let's make this full screen, and this is at oh, it's not auto-completing. Okay, add with carry to register, and add with carry to register takes register and addressing mode. Okay, so let's see our reference again. Can I make this to stay always on top? Task manager, can I make this always on top? Profiles, view, no, this is just information about the columns for this table. Okay, that's sad. From here, can I do it? Wow, I don't think I will be able to do it from here. Let's see. Values, provide feedback. Okay, nothing. I cannot make it stay on top. Okay, that's sad. So I will have to do something different. Let's try making it like this. Actually, this is a good idea because we can continue looking at it properly. So immediate is 69. So let's create some duplicates and let's fill the entire table with the same ordering. It's 65, 75, 6D. Actually, it's using uppercase here. I don't like that I am mixing uppercase and lowercase. So 79, 61 and 71. The arrow ACD, and let's see the bytes. 2 bytes for the first 3 bytes for the following 3, and 2 bytes for the last 2. Now let's change what is the addressing mode of each. This is 0 page. The second one is 0 page X. This is absolute. absolute x, absolute y, indirect x, and indirect y. Okay. And the last thing I have to fix is the cycles. So cycles is 2, 3, 4, 4, 4, 4, 6, and 5. Okay, this should be all. So now we can start making test cases. So because we have tested all the addressing modes, we should not need to test every addressing mode again. We should be able to just use immediate and assume the addressing mode is working properly, because we have tested it in LDA. But I already created different test functions, so let's go. So let's create a new CPU and function, and let's start it. So let's use this table. So let's find from the history this overflow txt, and there are a good list of tests in here. So let's make this these operations. So this one is made in binary with 4 bytes, but we can make it in 8 bytes, of course. So this is I want to load the binary 0, 1, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, one more, 8. And I want to add with carry 069 is the instruction we are testing with immediate, the same value and nothing else. So after this run, the B flag should be on. So after CPU flags.b should be true, and because this is not making a carry, should be false. Carry should be false, and this is dot value. Before I forget, carry should be false. Let's make carry before overflow, and let's see if this passes. Okay, I did not do it properly. Why is carry dead? One, 2, 3, 4, 5, 6, 7, 8. I am adding them. This should be 10000. Okay, let's execute it, I guess. This is what all is about, right? So, get the address, get the value. Value is 64. What? Oh, I see. Yes. No. The result is, of course, 128. Should be 128 plus 128, right? 64 is the maximum value. So that means I have an extra 0. I am a little confused, to be honest. This is 1, 2, 3, 4, 5, 6, 7. Oh, yeah, but so what am I doing wrong? This OXE0, OXE0 happens if I do this. Get the address is that odd number, the value 224 now. $448, and when I register it turns into negative value. What? That is obviously not right. So let's try to see it in the calculator. So binary 0 1 0 0 0 0 0 0. So this is the one I want. Is what I am writing. It's a 64 in decimal, a 40 in hex. So I made a plus and the same number, and the result is indeed 128. But why is it? Is the result cropping back again to 64? Let's see that. 1, 2, 3, 4, 5, 6, 7, 8. Let's try to make it work. So previous is 64. So that is wrong, right? It is not 64, is it? 1, 0, 0, 0, 0. Wait, this should be binary. 1, 0, 0. Oh, yes, it is 64. So you add, and the new value should be 128. Why is that happening? One, two, three, 4, 5, 6, 7, 8. Why is that happening? GdScript print binary. I want to print it. Forget that. I just want print in the binary. Can I make it like? Oh, this is a B, not an X. And how does it go now? Value is 64. Okay, it did carry this time. Assertion failed anyway. So what am I doing wrong then? Previous is 64, result is 128. The new register value is 64 in theory. And let's see the carry flag. This was 8 bits, not 16 bits. Okay. Wait. Did carry? Yes, this is 00. FF00. I want to check if something in the second half of the 16 bits is used. Okay, seems like it passed. Cool. Yay! So it's so good that we made this test, because otherwise I should not have been able to fix this. I am not that good with binary math. So again, where is my music? Moving on. So we only did one of these operations. Let's try more of them. Second operation is with the one in the other side, and this one will produce a carry. Let's type an overflow. Yeah, no need to create a new CPU. So let's go. Yep, it passed. That's cool. The third one. 101. So this is the second bit and the first bit. This will not produce an overflow and not produce a carry. The thing happens. So next is everything except the endings. Only the first and last. And this one should not create a carry, and also not create an overflow, because this will be a false one. And also this is a negative, so let's, because I am forgetting the zero and negative flag. So if this is non-zero and this is a negative, this is not negative and not zero. This is negative and not zero. And this one, looking at it, is non-negative and non-zero. Let's see if this passes here. Nope. Oh, this one is negative. Indeed. Yep, it passes. Okay, awesome. Oh, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and this is the last one we have to do. Is this correct? No. This is the last one we did. 2, 3, 4, 5. I did something wrong? Oh, this is twice. that is what I did wrong. Okay, so this is the first bit and the last bit alone. Okay, and this does not carry, does not overflow, is not zero, and is negative. Let's see if it passes. Indeed it does. and last one. So the first 2 bits in both cases. So this one does carry, does not overflow, is not 0, and is negative. Let's test. Okay, and let's make one more just to make it result on 0. So let's make it all ones and a 1, and this does carry, does not overflow, right? Because they have different values. This is 0 and it's not negative. Yep. What? It's not 0? Why is that? What is on register A? It's a 0. Then what happened? I think this is the issue. Yeah. Okay, so this is the issue. I should not test result, I should test the register value. I am glad I added that test. So now this failed, and this is because this one is indeed 0. I am adding a 1 and a 1, and this overflows. And now it passes. Oh! Okay, so now I have to repeat this for all the other functions. Oh dear. Copy and paste. Let's change the name. Let's change the instruction. 69 for 66. Now this is 0 page, and that means now I have to use memory instead. So let's see how I have used of memory before. So what I am going to do is have many values of memory and use one slot of memory for each of these values. So I will use over 10 in here instead. And now I can just use the other memory slots, so I don't have to write many times. So I can translate, move this from here to here, from here to here, from here to here. And now I can use 0x11, 0x12. I will copy this first part. 13, 14, 15, and 16. And let's see if addressing mode works. I did something wrong. I replaced this one. Should be 69. Okay, and it still passes. Meaning our zero page is working fine. I probably have much more test cases than needed, to be honest. So this is absolute. So I need to use second page. So let's add a 10 for everything and a 10 for everything in here as well. And let's change the instruction. Replace. Okay. And this one. Let's try it. Fail it. Because I am using big endianet instead of little endianet. You fool. Actually, it's not only that, I also use 2 different bytes. Okay, it passed. Cool. I will start collecting stuff. Let's go from the top to the bottom. Okay, that's smaller. And let's copy the content of this and start working on this one. So this is 0 page X. So let's make X equal to 1 probably. So let's load. Actually, we x is already a 0, so I can use increase x to have a 1 in it. So int x was double A. Let's check it. In x takes 1 byte and it's is 8. Okay, thank you. Before loading our values, we are going to set the value of x to 1. And now the rest should be the same, except, so this is the absolute x. So I will copy this before changing it and make it, put it in absolute x, because now I have to change it to be 0 page instead of absolute. So this one I need to remove all these x's, sorry, this 10, and I have to also remove all these 10. And now I have to change the command. So let's start replacing. And we have this one. So increase x, load the value, execute the operation with 0 page x with this memory location. 10 plus 1, it will use 11, and end the execution. So let's try it. Okay, it failed, but failed in the one that we did not finish. So it passed the OX75 ABC. And the reason why this did not pass is because I did not yet replace the instruction. So instead of 60 is 70. Let's start replacing. And test if it passes. And it does. Awesome. Moving on. The next one is absolute Y. So it's almost the same as absolute X. Copy it. Paste it, and now instead of increasing x, I will increase y, which is C8. Let's replace it. And this is 79. So let's change 70 for 79. If I am not wrong, this should already be working. and it passes. Awesome. And indirect X and indirect Y. Wait, I don't have 0 page Y. Right, there is no 0 page Y. Interesting. So the indirect ones are the hard ones. Let's see how we did indirect in other function. I need to remember how this works. So they are called indirect and indexed indirect. What does that mean? The instruction contains a 16-bit address which identifies the location of the last significant byte of another 16 memory address, which is the real target of the instruction. Oh, okay, so we need two values of memory. Let's copy this. And this is 0x0003, so let's see. For 0x03. Right. Nope. 5. No. 4. Five, 6, 7, 8, 9. So less significant byte, more significant byte. This is 4003. And now I have to make addresses for the other 3, 4, 5, 6. So this is 12, 13, 14, and move on. And 8 and this and this is 2, this is 4, 5, 6, 7, and I am missing 2 more, 8 and 9. So this is C, D, oops, E, and F. And this is an 8 and a 9, and I am missing a comma that I accidentally deleted. And I think this should do it. So let's see how I increase it X instead of Y. Wait. Oh, I am modifying the wrong. I have to undo all of this. Okay, I think that's it. And I will paste it in here. Let's confirm this is still triggering. Okay, I did not break the test. Awesome. Okay, so this is indirect X. Wait. Yes. So absolute X. I wanted to check for the increased X. So I will use that in here. Let's start replacing. The instruction is 0x61. Let's start replacing that as well. So now we have either X takes 1 or 2 bytes. It takes 2, right? Yes, it takes 2. So that means this should be in here. So now the only thing that I am missing to fix is changing this to be jumping from 2 on 2. 4, 6, 8. And it comes A now. A to A, okay. Yes. A and B. I am surprised that I am not losing track of this famous last word. 61 indirect X. I need to change this and give it a try. Okay, I broke something. Opcode 16. What is 16? Is a 10. What? Why it's trying to read a 10? Program counter. Okay, it's 8006. Mm, I don't think it's going to work. What was the value of program counter? Because this is in decimal. Okay, 32,774. Okay. Oh. I can navigate like this. Well. Let's find our program. 7074. Okay, here is the program. And we are in this memory location, but we have advanced. We have written a 16, which is indeed a 10 in decimal. And what is this program? Actually, we can find that out from here. Okay, it's the first one. So we are trying to increase the deck. Ah, that explains it. So the thing is, we are making the 10-10 thing here, and then adding one more. So can I maybe do this? Hey Korea, thank you for the follow. How are you? Let's add one. I hope it all works. Nope. Code is still 10. I'm failing on the very same one. Should be taking 11. Oops. 0x61 registered properly. ADC 61. It takes 2 bytes. Right. So that's why it's failing. It only takes the first because they are consecutive. I don't need the second one. So, a little context. We are writing the CPU for the NES emulator. We have a bunch of instructions. We have load, we have store in memory, we have set register, transfer register, increase register, and right now I am writing tests for the last instruction that I wrote, which is add with carry. So I have test for adding with carry for different memory access modes, and I am writing the last two versions, which are kinda difficult to be honest. And I think what I am missing is this, because now I am just taking the first byte and reading that on the next. Okay, it passed the first. And why is that? It's 12 plus 1. Wait a second. Why is a Q in here? This one should be 4, not a Q. Five, 6, 7, 8, 9. 10? No, it's not 10. 8. No, okay, this is not even needed. Oh, almost. Maybe. Right, this should be a D. Because it jumps in from 2 and 2. But let's give it another try. No, still failing. So A, B, it should be C, not D. Stupid. Went to the opposite direction. Okay, now it passes. Awesome. Ooh, that was hard. An indirect Y is even harder. Let's shrink this one. This one adds after. Actually, my music is stop it again. Okay, there we go. So I think what we want is add here instead. And increase register Y instead of X. And this is 71. Instruction 71. Could this be magical? It's magic! It passed on the first try! Can't believe it. No need for this anymore. Okay, cool. So it's done. Moving on to the next instruction. So the AND instruction. So this is a logical AND. A logical AND performance bit by bit. So this one is easy, and it affects the accumulator, 0 and negative. So it's very easy to do and test. So let's duplicate, delete, and operation. So let's actually copy the entire list. Nah. Just make bitwise and with register. Now I create this function with the register and the address in mode. We get address and value as always. Bar result int will be equal to p register the value and value. P register the value is going to be equal to the result, and we update 0 and negative flags. So we don't even need the result. We can say and equal, because the value should never be more than 8 bits. So it's safe. So how do we test this? Okay, before testing, let's register it, right? So, and the first one is the immediate. And let's duplicate this a little. And let's see what are our supported addressing modes. So the opcodes are 29, 25, 35, 2D, and 3D, 39, 21, and 31. Okay. And the addressing modes are immediate, zero page X, absolute, absolute X, absolute Y, indirect X, and indirect Y. So now let's see the bytes and cycles. The first 3 uses 2 bytes. The second 3 are 3 bytes, and the last 2 are 2 bytes. And for the cycle, it's 2, 3, 4, 4, 4, 4, 6, and 5. So we have this table copied. And we can start writing tests now. Writing test is what takes most of the time. Un buen amigo me dijo, en el mundo de la programación no se trata de llegar primero, se trata de llegar. Yo recién estoy empezando con la programación en Python. Éxitos y a no bajar los brazos. Hasta la próxima. Bueno, muchísimas gracias por pasarte por el stream. Ojalá lo hayas disfrutado el ratito que estuviste. Moving on. Test and oh, my keyboard is configured. Let's fix that. There we go. Test and bitwise operator. Oh, test and copy this and let's replace it fast. Let's remove this. Let's delete this. Change it to 1. Bitwise and now we have to copy again the opcodes. It's 29, 25, 35, 2D, 3D, 39, 21, 31, okay, looks correct. Copy, go to the bottom, paste, and start making massive changes. Okay, compiling again. Okay, let's search for something easy to copy, let's use LDA. Let's copy this LDA immediate. And start with the AND operation. So let's see, what operation are we going to do? 2, 3, 4, 5, 6, 7, 8. So this will be the first one. So we are going to load this value, and we are going to and this value, and the result should be 0, 1, 0, 0, 0, 0, 0. This should be the result. Non-zero and non-negative. And for now I will comment this and see if it passes. And it does. The next one, I will delete this one. One that causes a negative, that will be this and this, and it's negative but non-zero. Try it. Cool. And one that causes 0. So what I have to do is just change this to 0, 0. Let's make everything that is a 0 in the other side, a 1 in this side. And the result should be 0. And let's give it a try. It did not pass. Because I forgot to change this, of course, and it's also not negative. And it passes now. Okay, awesome. I don't need this anymore. And let's start moving on to the next. So 0 page means we are reading from memory in the first 2020 256 spaces memory, or 128, I don't remember actually. It's 128, yes, in the first 128 spaces memory. So how do I write memory? This one. So what I am going to do is invert the order so I can always use this one. So what I am going to load is what was the second operand, and now I am making an AND 0x25 to my magic memory address, which is 0x10, and forgetting a colon. This one should be done. Oh, it passes. Awesome. Okay, absolute. So it's almost the same, but we are going to use a higher page. So we are going to 1040. So we are going to access, because of little endianness, first a 40 and then the 10. And of course, change our instruction to 35. So this is absolute. Let's test it. And it did not pass. I did something wrong. Ten 40, 40, 10. What did I do wrong? I loaded. And what I am trying to load? It's trying to run the opcode 16. Why is absolute not taking 2 bytes? How does this work? Maybe 35 is not absolute? Oh, 0 page X. It's not absolute. Where is my 0 page X? It is here. Okay, so let me check this. What is wrong? What is 35? 35 is 0 page X. That is dangerous. Seems like I messed it up here. This one is 35 and this one is 2D. And now I have to fix this function signatures 2D 35. No, wait. This is 2D and this is 35. Zero page X comes before. Okay, so in here I am absolutely basically the 2D, so I will just do that change this by 2D for the absolute. and see if it passes. Okay, it does. That was dangerous. Oh, my dogs are barking a lot. I will mute the microphone a second. Be right back. Here we go again. I hope they stop barking for a while. So, we want to increase X. Let's say X was C8 or E8. Take a look. Increase X with E8. Oh, X D8. So now X is a 1, and we can use the instruction 35, and its 0 page should take only 1 byte, and we want to put 09 here, so we can use the address 10 here. So it will be 9 plus 1, 10, and it will read this boolean. Let's give it a shot. And it failed. What did I do wrong? What is register A0? What? Did I do this wrong? $35 is 0 page X. Sorry. Increases X. X right. E8. Okay. Increase X. Loads the value of always, and then instruction 35, 09, right, because it's not 09, it's OF. I keep thinking in decimal. Stupid. Okay, now it passes. Move on. Okay, no 0 page Y, so we go to absolute X now. This is very similar except 2 bytes memory. So we can look at 1040 in example, or 1041 actually, because we are going to increase one. And let's see, the instruction is 3B, and the address we want to check is OX40. The second one is OX10, and this is because of little endianness, of course. And in theory this should be already working. Let's give it a try. And it passes. Let's fix this print for a moment. This is correct, and this is not correct. Okay, and I think that's all. 25. Okay. Okay, we have absolute X working. Let's go with absolute Y. In this one we are going to increase Y instead with C8, and the rest should be all the same except of the instruction 39. And change the print and give it a run and pass it. Okay, indirect X. So I like it what I did in the other side because it makes much more obvious what was happening with the memory. So you have the memory address. So this is a pointer to pointer. Let's copy this. And let's copy this entire thing and paste it here and erase everything that we don't need. Part. So, and this is the value that we want in here, and we can close it. So what is happening here? And we are going to read. This only takes one argument, sorry, 1 byte, which is the 10. The instruction is 39. Wait, oh, I am changing the wrong one again. Okay. Okay, now let's see. It's 21. So we increase X. So this should be E8. And load our mash value, and then make indirect X access to our 10 plus X, that is 10 plus 1 memory address. So let's try it. And we change the print and does it fast. Okay, awesome. So now we make the indirect Y, and to make the indirect one we should remove the plus 1 from here and put it in here, and that makes indirect Y work already. Now we have changed the instruction and change increase X for increase Y. And let's try it. It's perfect. Forgot to change the instruction. Okay, awesome. And it's complete. Isn't that cool? Okay. So let's make a commit with all with everything we did. I will put this over here and open a bash and console. Git status, we change it only 2 files It's this. And we added ABC and AND operations today. It adds in parts, declaration, implementation. Oh, the new update flag, new test. So git commit implement ABC and instructions and create for them. Git push origin main. Oh, awesome. If you want to check the code, you can look for it in GitHub. So I am uploading this to my studio repository, and it's called Game DLA. I'm going to put this in the chat. Okay, this is all for today. Hope you have enjoyed it. We did a little progress. Yes. Hope you have enjoyed it. Hope you want to come back again the next time.